Okay. So first of all, welcome to everyone. Obviously, it's your first sessions because it's the start of year 11. It's always an exciting time because it's something completely new. I will say that the step up from year 10 to year 11 science in all your sciences, whether you're doing chem, phys, bio, whatever it might be, the step up is significant. So just keep that in mind that what you've done in the last 2 years is probably going to feel like not as much by the time you reach the end of this year. And again, at the end of year 12, you'll feel like, oh, what I did in year 11 wasn't actually that much. But the point is right now that change will be very big. So it's a pleasure to welcome you all. It's going to be a long 2 years for you all, but hopefully along the way, you'll find that you grow as students, grow as people, and you achieve some of the goals that you set out for yourselves. So one thing I always ask at the start of these sessions, and I may have talked to you on the phone, if not, we'll talk about it now, is what is your dream at the end of all of this? So why are we actually doing all of this study? What's it for? And for some of you, it's medicine. For some of you, it's a different degree, dentistry, some of you want to go abroad. So whatever it might be, having a dream in mind will be the only thing that's going to keep you disciplined enough to get through these next 2 years well. If you just are doing this for the sake of feeling like you should study hard, that's not going to last. So make sure that at the start of this session, you have thought through at least what your dream is and know what your goal at the end of all this is. And that will help you work backwards to find out what your dream ATAR is if you haven't already figured it out. For most of you, what you want to do in the future from what I've spoken to you about is something STEM related. You want to do something sciencey, whether it's, as I said before, a science degree or something more health related. So doing chemistry will directly benefit you in these fields. And it's why it's so important that taking chemistry and you doing well in chemistry will actually help you in the long term as well. So just to get an understanding, first of all, of how you guys have been studying, I'll start with Zena, if that's all right. How would you describe the way that you study sciences? How would you describe it?
Um, Usually if I have trouble understanding a concept like during class, I'll look through it at home, like that day, and then on the way on a say on like a Saturday, just do a quick overview of just everything what we did that week.
Nice. And then so that'd be every week. And then when you approach exam period, how would that change?
Uh, this year I didn't do this last year, but this year I'm trying to do like overviews for like every topic we do. So then I
Hmm.
don't have to look through all my notes. So then I've got like a, you know, overview of everything done.
Yeah, cool. And Martha, how does that differ for you? What do you do the same? What do you do differently?
So I think I adapted the same method last year, but I usually take my notes from, oh no, not the notes, I guess the booklets and the textbook and all what we did throughout the lesson. And I try to summarize it in like a notebook or maybe view some videos on anatomy and try to understand the concept better.
Yeah, great. And Soha, anything else you'd add?
Well, I used to not like really take good notes, so it like made me struggle like studying for tests. So like I kind of improved that. So taking
Mm,
notes, reviewing over them over like parts that I need to, and yeah.
yeah, okay, great. So it sounds like for the three of you, notes are quite a integral part of the way you study. You all seem to put together your notes and you're planning to do that this term. And that's great. But I'm going to be the first one to say I'm a firm believer in not making notes comprehensively each term. And I know that's going to sound really jarring, and you're probably going to hate me for saying it because it goes against what you've learned and kind of developed over time. But making notes takes a lot of time. Would you agree?
Yeah.
Making really good looking notes takes a ton of time. And at the end of the day, when you're making notes, all you're doing is laying out information in a way that, again, it makes sense to you. It's going to help, but you're just rearranging information, right? Are you internalizing that information? Probably not as much as some other people who use other methods, but it's a good start. It's a good start. So what I want to try to shift you away from, and in particular with chemistry, because my job should be to provide you guys with the notes that are already made and ready to study from. That's my job. If you guys have notes that are already made, you can, of course, take the important things from these notes and rearrange it yourselves. But for the most part, my notes should be able to take care of that note making for you. So that means that after we've covered content, your job is not so much to rearrange notes and spend your time doing that. It's more to spend time actually internalizing the information and understanding it. So we'll talk through my 3-step model that I kind of came up with over the last 3 years that helps my students do well, better, understanding their STEM subjects. And it comes in 3 phases. The first stage is awareness, and it's understanding content for the first time ever. And this can come from either me, it's most likely going to be me. It could be your school teacher, and it can also be online resources. So when you're reaching awareness for the first time, your goal should just be to understand stuff in the moment and understand everything in the moment. So as soon as you become confused, your job is to ask questions and accept that you're confused, because no one is going to learn everything on the first time through. I'd expect, for the most part, you guys get lost during my lessons. That is the whole point. You guys are meant to ask questions. You are meant to admit to yourselves that I'm a little bit lost here, because that means I'm not doing my job as good as I could be. So you got to let me know that I'm not, and I can help. So during the sessions, first task, understand everything for the first time. Tell me when you're confused, and I'll explain things better. From the first time through, I always ask students as well, how much do you think you retain an hour after the class? And a lot of students will say, 60%, 70%. Are you guys around the same, or would you say higher or lower? What's the mood?
Around there. Yeah.
Around there? So for me,
Yeah.
yeah. For
I guess
me,
a few 80s. Yeah.
yeah. For me, if I'm being completely honest with myself, I would say I retain about 33% of what I learned on a first pass. And that's being pretty generous. If you ask me an hour later after a class to recall things from the class, I'll probably say I can explain about a third of the content pretty well. The other 2/3 are quite blurry. Why that's important? It's because the sooner you admit to yourself, the first time you cover content, it's probably going to be terrible. The sooner you'll be able to lock into the second stage, which is actually reaching the understanding of that content, going through it in your own time and solidifying it. So here in this second stage, understanding, your job should be to actually internalize this information and be able to recall it from the depths of your brain. And a lot of people hear the phrase active recall being thrown around. Have you guys heard of active recall? Active recall. So basically all that means is you're constantly testing yourself to see if you can dig information out from the back of your head. And the way you should be studying is using a method that constantly forces you to recall that information. So for example, note taking, if you're just making notes, you'd be transcribing notes across. It's not actively trying to dig information out. An active recall method, for example, would be mind maps. If you are starting on a blank piece of paper and trying to write everything you remember from a topic, that is actively recalling from the back of your mind. If you've got a table and you're trying to remember the 2 columns, you cover one side and you're trying to remember across, cover and check, that's active recall. So if you haven't started using methods like these, I would probably recommend that you give them a try this term as you start to understand what works well for you. There's no right way to study, and I can't emphasize enough. For some people, honestly, note taking is actually the most efficient way for them. So if it is for you and you find that after the end of this term, next term, the end of year 11, stick with it. It's fine. But I will say that if you can incorporate active recall and these methods into your revision, you will feel that content sticks better. It just sticks. Okay. So these first two stages is where I think we're focusing most on. But there's a third stage that students in year 11 have to really start stepping up on. And it's called becoming exam ready. Becoming exam ready. You can study a subject all you want and reach great understanding of the content. You can really understand it well. But when you go in an exam, oftentimes you're getting asked questions which are very repeatable and have exact marking guidelines. They don't differ very much from year to year. In fact, they hardly do. So if you're going to an exam and you've never done practice questions before, you're essentially guessing what your marker wants from you. You'd be guessing. So the only way to make sure that you can guarantee you turn your understanding into marks is by doing as many practice questions as possible and marking yourself harshly on these questions to ensure that you get full marks. Practicing under time conditions as well helps, so you get used to the exam environment. What's the longest exams you guys have done up until now?
About 50 minutes an
50
hour.
minutes?
Yeah, same.
Same? Soha?
An hour and 30.
An hour and 30. Yeah. So it'll be moving up from here as you start to move into year 12. I'm not sure if you know yet. The final HSC exam, how long do you think that is for chemistry?
2 hours.
2 hours? Zinat, what do you think?
2.5 is what I said.
2.5, Soha?
Probably 2 hours.
3. 3-hour exam.
Wow.
So if you don't start to build up your endurance and concentration and focus, you're going to feel lost by the end of this all. Year 11, you're not going to hit 3-hour exams. Don't worry. It's not coming yet. But just have an idea of how these exams are going to ramp up over time and how if you practice these exams, you will get better and better and better. So this term, that's why I give you guys an exam each term. This term, you'll have an hour and a half exam with me. That's all we're working towards in week number 7 is an hour and a half exam for just module 1. So each session, yes, you've got your school exam, but you can also be preparing for my one. And after you've sat my exam, you'll be more confident for your school exams as well. Does that kind of make sense where we're working towards? Great.
Yeah, makes sense.
Cool. Any questions on this framework, first of all? Because I think for the most part, you guys are focusing a lot on the second stage and doing it pretty well. But the third stage is where you'll have to work on more. A lot of practice questions and exam readiness. Okay. So that's the first kind of broad overview of how to study. I also want to give you guys a few more chemistry specific study techniques. So this is from the study guide that I've written up. I just want to draw your attention to, first of all, not this one here, this page. So up until now, you guys might have been given a outcomes booklet or a small syllabus from your school. Yes, no? That tells you what to study each term. Yeah? Yeah? Now, the whole state follows the same syllabus. Everyone learns the same things now. From year 7 to 10, each school sets their own ideas that they teach. From year 11 to 12, the whole state learns the exact same thing. So this document, the chemistry stage 6 syllabus, if you search it up in Google now, it's like chemistry syllabus. Just search it up because it's an important doc. It should be the second PDF that comes up.
So say it again, please, or shall we switch
The
it up?
chemistry New South Wales syllabus or chemistry stage 6 syllabus. It's like 2000, it's a 2017 doc that comes up.
The year 11 one?
It should be like the whole thing. The cover page looks like this green
Okay.
page. Give me a thumbs up when you've gotten this up.
I think I got it.
Got
Is
it?
it to 2017?
Yeah, 2017, it's like 50 or so pages.
Okay. Got it.
Mm. Oh, yeah.
Yep, got it. And Soha, got it
Yep,
as well?
got it.
All right, perfect. So the first half of this document is waffle. Don't worry about any of that. You only worry from about halfway down, where if you scroll all the way to module 1, about halfway down, from there it's pure gold. So scroll until module 1.
Um,
It's about just past halfway down. Say like module 1, properties of matter.
do you know
Property.
exactly what page it could
Let me
be?
find it. That's okay. Let me find it.
It's page 36.
Okay, yeah, I got it.
Got it?
Yeah.
So how you got it as well?
Yeah, got it.
Okay. So if you look at this page and you scroll down to the next one, there should be some inquiry questions and some dot points underneath a few inquiry questions. Each of these inquiry questions tells you exactly what your school can assess you on. You can basically think of it as illegal for your school to test you on anything outside of these dot points.
Mhm.
So if, in theory, you study all of these dot points and do questions around these dot points to have hit every single one, there's nothing your school can throw at you that you haven't already seen, right? So this document is so, so important. Use this as the document that you base your study around, and make sure each time you prepare for a module test that every dot point is covered up to where you're up to. That's the best way to be comprehensively ready. Yeah. So the big understanding is just knowing that the syllabus in chemistry and any of the sciences is completely finite. It's controlled. You won't get assessed on all sorts of far-reaching things. If you know the stuff in the syllabus, you're going to be good. And then if you're going through and studying the syllabus dot points, for example, this is module 1, inquiry question 4. So this is what we'll be learning at the very end. If you're going through and studying all of these things and you're ticking off dot points and you realize, oh, I have no idea what this is, that tells you what to study. You study that dot point which you just didn't understand. Cool? All right. And then the very last thing I want to show you before we start is the method that changed my chemistry trajectory completely. So before I used this, I was maybe a average-ish, just above average student. After I started using this, I ended up finishing first in my school. So if you can take anything from that, and my past students have also used this method works. It works. And all it is keeping track of your mistakes through this next 2 years. Keeping track of your mistakes. This applies to any subject, but in chemistry, particularly powerful. The way I want you to think about it is through how your brain works. This is a bit of a neuroanatomy coming in from my med degree, but I'll teach it to you anyway. So your brain is an organ which recognizes things that it likes and things that it hates. One of the things that it hates is pain. If you think in your brain, when was the last time I really hurt myself? That memory is probably very vivid. And there's a good reason for that. Because if you hurt yourself or injure yourself, your brain is going to do everything in its power to make sure you don't do that again. Does that make sense? So if I burnt my hand on an iron when I was 5 years old, my brain is going to have singed in its memory the sequence of events that led up to me reaching up and touching that iron. And it's going to tell me, no, don't do that again. That's stupid. So why don't we do the same for studying? And the reason, there isn't really any reason why not. So we should. How do we do it? Keeping track of your mistakes. When you make a mistake in chemistry, physics, bio, that is a good thing. I'm going to reprogram that understanding. If you make a mistake, and it's obviously not in your exam, but before your exam, if you make a mistake, that is a very, very good thing. It means you are understanding things you don't understand. So if you keep track of all your mistakes in one place, you are telling your brain, these are the things I must not do again. The same way your brain creates the memory of not doing things that cause you pain, You want to make your brain feel like making a mistake is pain, and you program that as something you don't do again. Does that kind of make sense? It's a bit abstract.
Mhm.
Yeah. Okay. And the way that I found worked really well is a very simple method. It's essentially ugly flashcards, but it's what I call a question solution table. So in your left column, you're going to keep all your questions, concepts which are misunderstood, and in the right, you write out the solutions straight away so that you have the question that wasn't understood, and on the right side, you're solving your problem, giving yourself the solution for the next time you come across this. If you do this from the start of year 11, you will be unstoppable by the time you reach the end of year 11. Because I only started this halfway through year 12, and the students I start this with from even midway through year 11 will reap the benefits at the end of year 12. So if you guys start now, it compounds over time. Things that you've messed up will be so quickly resolved that by the time you hit your year 11 exams, it'll be second nature and it'll be ingrained through year 12. Does that kind of make sense? So every time you lose a mark, even half a mark, a question goes into the question side of the doc, explain it to yourself, write a solution out, and then the last thing that's so good about this table is that all your mistakes and misunderstandings, guess what? They're now just in one place. So instead of going through and studying notes and going through the whole module set of notes and spending so long on that, if you just study this table and test yourself on the questions that you messed up again, you are testing yourself on things you definitely don't understand. It is more efficient. You are testing yourself on things that are misunderstood.
Mm.
And that's why this works long term as well, because then you can always come back and revise this table. Does that kind of make sense? Fair enough?
Yeah.
Yeah. Although, where could we find these questions? Could they be from like practice tests or like that, you mean? Yeah.
Anywhere, anywhere. So if you've done
Yeah.
practice tests at school and you've gotten
Yeah.
corrections from your teacher, write them up.
Yeah.
If you're
Mhm.
going through a textbook and you messed up a question in your textbook, put it in. If we're going through something in class and it doesn't make sense, put it in. Ask me the question. I'll try to explain it to you as best I can.
Mhm.
If you accumulate mistakes, you are accumulating learning. That's the way I want you to think about it from now.
Yeah.
Collect your mistakes. They're valuable.
Mhm. Makes sense.
Okay. And this study guide has a bunch of other tips in it, but these are the main ones that are going to be very chemistry specific and will be high yield if you start straight away. So without further ado, I think it's time we start our content for today. Okay. So module 1 is the properties of matter, and you'll be exploring what different properties of matter are, what atoms are, what radioactivity is, what the periodic table actually is for, how does it map out trends for us, and finally also bonds, what holds atoms together. So as a brief overview, that's what we're covering. Don't worry too much about understanding everything all at once. These concepts are kind of disjointed. So what you will find weird this term is that you'll be learning one thing and it sort of jumps somewhere else straight away. And you kind of just need to learn chunks. They don't fit together perfectly. So if you're happy with just learning a chunk, understanding it well, learning a separate chunk, separate chunk. It's a bit like that this term, unfortunately. I tried to make it as sequential as possible, but there will be a bit of jumping. Okay, so let's get started. So there is a bit of assumed knowledge from years 7 to 10. If your school hasn't gone through it yet, that's fine. But these are the things I would hope we sort of already understand before we start year 11. So first of all is the states of matter. We have 3 main states we're taught, which are solid, liquid, and gas. And I always like to model these with my hands. So if I have a solid particle and it is in a lattice, I always think of solid as just vibrating in place. Solid particles will vibrate in place next to each other, and they can't escape the attraction of the molecules around them yet. How are we going to get them into a liquid state? How do we turn solid to liquid?
You did?
Heat it, right. So what does that do? What does that give these particles?
More energy?
More energy. And what specific type of energy? It's
Heat energy.
Heat energy, which turns into kinetic energy. So we have movement of these particles, right? And as they go faster and faster and faster, eventually they can't hold each other together anymore, and that's how we become liquid. Does that make sense? That little model with I'm doing with my hands. So we're now liquid, freely moving. But these liquids, if you have your cup of water, they can't escape the liquid state. So as soon as they get to the top, the surface tension and the attraction pulls these particles back down. So even though they can reach a surface, they can't quite escape. So then again, how do we turn from liquid to gas? Moving, and then we just apply more energy so that bang, particles now can escape. That's how you turned it from solid to liquid to gas. Does that make sense so far?
Mhm.
So the states of matter, solid, liquid, gas, they're separated by how much heat energy our particles possess. Then we have a method called the crisscross method. Don't have to know this method. A lot of people understand it just intuitively. But when you're making a compound between a metal and a non-metal, we call that an ionic compound. And the way that we figure out how many atoms of each is through a crisscross. So for example, if we have a magnesium ion bonded with a magnesium bonded to chlorine in an ionic compound, the way we figure out how many of each atom we have is by using their valencies. Does everyone understand what valencies are?
Is it in the atom, the outer um cell, the amount of electrons?
Yeah, basically. So if you were to complete that outer shell or completely empty it, it'd be the charge that remains. So for a metal, because most metals will either have one or two electrons in the outer shell, if they were to give away that electron and hence form an ionic bond, that's for the ionic compound, it's the charge that that ion would be left with. So let's take Mg as an example. It would have two valence electrons in its outer shell. If it gave away both of those electrons, which are negatively charged, so you've lost an E minus and an E minus, the magnesium is therefore left with a 2 plus charge because it's lost two negatively charged electrons. Does that make sense? So that's how you get your valency. And then for a non-metal like chlorine, its outer shell has only seven. Only seven. So if a metal donates an electron to this chlorine, then its outer shell is complete and it's gained an electron, so it ends up with a negative charge. That's how we get those valencies out. Does that make sense? Okay. And the way we figure out these valencies is if we're bonding magnesium, for example, which has 2 plus valency, and chlorine with 1 minus, we do a crisscross so that magnesium's valency ends up as 1 and chlorine's, or not valency, magnesium in this compound, there will be 1 magnesium and 2 chlorines. Does that make sense for everyone? Any questions on this? Or is this understood? Soha, okay?
Yeah.
Any questions?
Wait, so it would work with anything, right?
Any metal and non-metal. Good question.
Oh, okay.
Any metal and non-metal. So if I gave you another example, let's say sodium and chlorine. You can use the periodic table if you need. What would be the valency of sodium and chlorine?
One. Oh,
You say 1? Someone say 1?
chlorine. Yeah.
Chlorine is,
Yeah, chlorine is -1.
yep, -1.
And
And
sodium.
what's sodium?
Just getting up the periodic table.
That's all right.
Would that also be a 1 too?
Correct, good. Sodium also 1 plus. So the way you can tell on the periodic table, there will be these first two groups. This will be 1 plus. This will be 2 plus on the metal side. Then you have a bunch of these weird metals we call transition metals. We can't really know. And then you end up with a 3 plus, a row that we don't really talk about, and then 3 minus, 2 minus, 1 minus. And the very end row on the nonmetals are what we call noble gases. These don't have valency. They already got a full shell. On the very end is no valency. Sorry, I kind of ran out of space. So what would NaCl be in its arrangement if it was bonded together?
Just NaCl.
Yeah, because if you cross them over, you end up with 1, 1, and you end up with NaCl. Let's make a harder one. What about aluminium oxide? Aluminium and oxygen. What are the valencies of these?
Would oxygen have a -2 charge?
Correct. Oxygen has a 2 minus. And what about aluminium?
Three.
3. Aluminium is 3 plus. So aluminium is just to the right of those transition metals in the middle. So then what is aluminium oxide's formula?
Al2O3.
Perfect. So you're crossing them over and crisscross, and that's it. Make sense?
Mm-hmm.
Yeah.
So all you need to do, figure out the valencies, cross them over, and you can figure out the configuration for any ionic compound, which is, to be clear, a metal and a non-metal. Any questions on this? Cool. Who's seen polyatomic ions before? It's okay if you haven't. Hands up. Yes, no. Yes, no. Yes, Martha.
Yep.
Okay. So if you haven't seen them yet, these are something you will become very familiar with soon. And these are high yield. I would say that I would want these to be learned ideally by the end of this term from memory. The ones that aren't so important are these ones. I'll cross them out so that you don't waste brain space. But the rest of these, basically essential. These are basically essential. So what you'll notice about each of these polyatomic ions, polyatomic, meaning multiple atoms in each of these ions, most of them have a negative charge. The only exception is this ammonium, which has a +1 charge. So they all have negative charge except for the ammonium, which has a +1 charge. What you'll need to know for each of these polyatomic ions is 1, their name, 2, their formula, and 3, their charge. So this would be the first instance of getting you guys to try some active recall. So I'm going to give you 30 seconds to try to remember as many of these ions and formulas together. Ready? Go.
Without the crossed out ones.
Without the crossed out ones, yeah.
Okay.
Give me another 10 seconds. Okay. First of all, we're going to go from formula to name. So starting with ZNAP, what is NO3 minus?
Nitrate.
Nitrate. Martha, what's SO42 minus? Try not to cheat. It's okay if you don't know.
Yeah, sulfate.
Sulfate, good. Soha, what's PO43 minus?
Phosphate.
Phosphate. What's CO3 2 minus? Zena? Ooh,
Cobalt? I don't know.
not quite cobalt. Cobalt, it's a good idea. Cobalt is CO with a little o, but these are polyatomic ions. So we'll
Yeah.
come back to this one. What's the next one, Martha?
Something with I hydrogen, something? I don't know.
Hydrogen, yeah, hydra something.
Yeah.
We'll keep that and come back to this one too.
Mhm.
Soha, next one.
Oh, is it ammonium?
Ammonium, good. Don't worry about CN. And anyone for the last one?
Acetate? Acid?
Acetate.
Mm.
Great. Okay. Coming back to the ones we didn't quite get. Does anyone know CO3 2 minus?
Carbonate?
Carbonate. Carbonate. And OH minus, we got the hydro part, but the ending is,
Oxide?
yeah, hydroxide.
Mm.
Good.
Right.
So we've got this list of names out. But what I wanted you guys to feel in that moment was the feeling of digging information out from the back of your head. Because I told you to read this list for 30 seconds. About 30 seconds. How much of it could you retain? Probably about 60, 70%. And within an hour after this session, probably 30%. Right? So being realistic with how good your memory is the first step to getting good at studying, being honest with yourself. And then the hard part, can we go from ion name to formula? I'm gonna give you another 30 seconds. Going from ion name to formula, go. Okay, let's change up the order. We'll go from Soha first. What's nitrate?
Oh, NO3, and then
NO3
charge is minus.
minus. What's sulfate, Martha?
SO4 2 minus.
Nice, good. Zenat for phosphate.
NO4 -3.
Got the O4 -3. What was the first letter?
Oh, P.
Yeah, P. Good. Back to Soha.
It was CO3, and then I think it was a 2
2
minus.
minus. Good. Good, good. Martha, hydroxide.
HO, I'm thinking 2.
Good effort. We got the H and the O, and we said 2. The only changes, it's
Mhm.
actually the other way around. OH and then minus.
All right.
Got it?
Mhm.
Okay, we're going to come back to that one. Okay, lock that one in. And Zenat, ammonium. That's weird. Open to the floor.
Is it NH4 or 3?
What do you think? 50-50.
Not
And
too sure.
Someone take it. 50-50.
I think it's 3.
3. Anyone going to debate? Anyone going to be brave and challenge?
maybe 4.
You would have taken 4. So Soha, your friends have told you 2 different answers. What are you going to settle on?
I 3, I guess.
3. It is actually 4. So
Oh,
my
okay.
memory wins. NH4 plus. And lastly, acetate. Someone knocked this one out of the park.
I think it's CI, a number that I'm gonna get back to, and COO.
Uh-huh.
And for C, the number is 3.
3.
And I think it's -2 for COO.
Just minus. So it's CH3COO for acetate. And
Yeah.
everyone remembers this as chiku. Chiku. Makes it a little bit easier. So if you can find little funny ways to remember things, always helps as well. But for the most part, I'm pretty happy. We've gotten a gist of the names and the formula. So I'm going to leave you guys to spend some time and remember this on your own as well. It's not going to happen overnight. Just spend 5 minutes just memorizing these. 5 minutes every now and then. But yes, I hope you guys understood what I meant a bit better by active recall. It should feel like what you just experienced throughout most of your study. You should find ways to make your study feel like you're digging information out of the back of your head rather than just rewriting things or reciting things. Okay. Good. Diatomic molecules. Some molecules exist in pairs because they're just more stable like this. The easy way to remember this is any molecule ending in gen or ene will exist diatomically, meaning 2 atoms together. So that means all your hydrogen, nitrogen, oxygen, and then fluorine, fluorine, bromine, iodine. If it ends in genene, then it's going to be diatomic. Any questions on this? Okay. And lastly, balancing chemical equations. How comfortable are we on a scale of 1 to 5 balancing equations? 4, 4, Martha, 4, 4. Okay. So I won't go through the example. I think we're okay. But we will do some practice ones. So first of all, can you guys all balance Fe plus O2 going to Fe2O3? Feel free to write whatever you need. Use working.
Would the Fe have a 4 in front of it? And the O2 have a 3? And then the
3.
product would have a 2.
Are we in agreement? Martha and Zinat?
I don't know how
Yes.
that happened.
Don't know how that
I
happens.
don't know how to do it. I don't know.
Okay, no, that's okay. Let me show you the thought process. So when we're balancing equations, the only thing that you need to make sure happens is that both sides of the equation have the same number of atoms of each element. So at the moment, if we look at this equation, there is 1 Fe and 2 O's on the left side. And on the right side, we have 2 Fe's and 3 O's. So are we balanced at the moment, Martha?
No, no.
No, we're not balanced because there's too many iron and too many oxygen atoms on the right side.
Mhm.
So what can we do? We can increase the number of atoms on each side. So the left side, let's say we want to first fix the iron problem. So we're going to double the amount of iron to fix that. So we end up with now 2 Fe, and that's the iron is now balanced, right?
Oh, right.
But now we need to balance the oxygen as well. And we run into a bit of a problem because if we were to double the oxygen, we'd end up with too much oxygen then. If we went 2O2, now we have 4 oxygens. It's too much.
Mhm.
So then we need to increase how much oxygen we have on the other side. And the only way we can do that is doubling this side as well, which brings us to 6 oxygens and 4 ions over here. And now we have another problem. Now we have too much oxygen on the reactant on the product side and too much oxygen and too much iron. So we need to fix the other side again.
Mhm.
So the only way to fix it is by making 3 O2 to give us 6 oxygens and 4 Fe to give us 4 ions. And now we're balanced.
Right.
Does that make sense?
Yeah.
Okay. So have a go at the next one underneath as well, Martha. And everyone else, have a go at this one. N2 plus H2 goes to NH3. I'll get Martha to give the answer to this one.
Just a good question, because I get a bit confused sometimes.
Yes.
When you already have a number, like say N2, it already has a number and you're trying to increase it and you put a number in front. Are
Yeah.
you multiplying those numbers or are you adding those numbers?
You are multiplying. So
Yeah.
you are saying that you have two, by doing this, you are saying you have two of these
Yeah.
units. So then if you were to say you had 3 N2, you have 3 of these N units. So you're multiplying 3 times 2. Does that make sense?
Yeah.
Great, good
Oh,
question.
right.
Yeah,
Oh,
I always
yeah.
get confused with that.
Yeah.
Is that what? Okay. Okay. Good question.
Yeah.
And that's what I mean by ask questions whenever you get confused, because there's a good chance other
Mm.
people are lost as well. Just feel free to ask at any point. But how are we going with this one, Martha? How are you feeling?
I haven't done anything. I don't know.
That's okay.
I need some more explanation, I think.
Okay.
Yeah.
So at the moment, how is this equation currently unbalanced? What's not balanced?
Um,
There's no, yeah.
yeah.
The
The
hydrogen.
yeah.
Not enough N? Agree?
Yeah.
And then do we have too much or too little H on this side?
Too little, I think. On this
Too
side,
little.
I have too much.
On this side, too much.
Yeah.
So to fix those problems, what can we do?
Mhm.
We could, first of all, try to make the number of N's correct.
Mhm.
So how do we make them correct?
Put it to it.
Yeah.
What do you reckon?
We put it
We want
to
to, yeah. So in order to make 2 nitrogens on the right side, because we only have 1 at the moment, we can double the amount of nitrogens by placing a 2 in front of the NH3. What this 2 means is we now have 2 NH3 molecules every time this reaction happens. Does that make sense? Instead of 1. So
Yeah.
now we have 2 NH3. This means we have 2 nitrogens. Are we balanced completely now? Yes or no?
No.
No. Why not?
We have the hydrogen left.
Correct. How many hydrogens do we have on the right and how many on the left?
On the right, we have 3. Well, we have one of each, but what does the bottom number say? Like, what does that
Oh,
mean?
don't worry about the bottom number. I'll just say how many nitrogens there are. Oh,
One.
wait, sorry. Do you mean the 3?
Yeah.
So the 3 tells us for every NH3 molecule we have 3 hydrogens.
Oh.
Does
Also,
that make
it's
sense?
like for each of one, like it tells us the number.
Yes.
And
So,
the front number is for everything.
yes. So NH3 tells us that every NH3 molecule will look like this, with 1 nitrogen and 3 hydrogens.
Oh, okay, yeah.
And then when you put a 2 in front of that, it means you have 2 of these molecules.
Oh, okay, wait. I want to write that down. Um,
And we're joined by Huzaifa. Is it Huzaifa or Muhammad?
You can call me Joseph.
Huzaifa. All right. Oh, the camera. I think the camera might not be working.
Yeah, I'll fix that.
Cool.
okay, I think I got it.
Got it?
Yeah.
So then what do we need to do to balance the rest of this equation?
Right.
you need it. So that's 6.
What's still unbalanced, Martha? Because we have now how
Would
many
it
nitrogen and how many hydrogens on this side?
Okay, so we got 3 hydrogens,
3 hydrogens, but how many molecules do we have total?
2.
So then how many hydrogens do we have as a whole?
4. Wait, no, we got, hold on. Since we got, no, it's 6. Yeah.
6. Good. 6
Right.
hydrogens. Does that make sense?
Yeah, yeah.
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 So then what do we have to do to the left-hand side to make this balanced?
We put a 6 on the hydrogen.
If we put a 6, how many hydrogens do we now have? Because this is a HH.
Yeah.
Because it's
Oh, right. Oh, it makes sense. So we just put a 3.
yes, good.
Oh,
Great.
okay, it makes sense now. Okay.
Okay, good. Good, good, good. And Mohammed, how comfortable are you with balancing equations?
Okay.
Good?
Yeah.
Okay. Let's have a go at a harder one. Let's have a go at a harder one. Let's try number 1. This equation might be familiar for biology students. Everyone have a go at balancing this. Okay. And you got an answer? Thumbs up. Everyone got an answer or still working?
still working?
Still working. Okay, give you a bit longer. Okay. I might just explain it because this one can get very confusing if we make one mistake with balancing. So what you'll notice about this equation is we have some elements that occur on both sides of the equation. So the ones that occur only once are carbon, they occur once on each side. Hydrogen, hydrogen occurs once on each side. But what do you notice about oxygen? Oxygen occurs like everywhere. It occurs on twice on both sides. And with any balancing of an equation, you want to look out for these elements. You never want to touch the elements that occur on both sides first. You always want to leave those last. Does that make sense? So what we do to balance this is I look at the ones that occur once on each side first. So carbon, let's start with that. I have 1 carbon on the left-hand side. I have 6 on the right-hand side. So the logical thing to do here is make 6 carbon dioxides so that I now have 6 carbons and 6 carbons. Does that make sense to everyone? Any questions on
Yeah.
that first? Good. Then we have 2 hydrogens versus 12 hydrogens. What's the logical step here?
6 at the front as well.
Perfect. 6 out the front. So now we have 12 hydrogens. And now we're left with just our oxygens, the problem element here. So on the left, we have how many oxygens? Who can give me a number?
3.
How many?
3 on the
Careful.
left.
What are we missing out?
Oh, 6. I mean,
Yeah. Oh,
2 plus 8.
A? We're getting closer.
18.
18.
Oh, because there's
Because
2.
it happened twice, right? We got
Yeah.
double tricked. So we got 12 oxygens and we got 6 oxygens. So we have 18 all up. Does that make sense, Martha? How we got there? And Mohammed also following.
Yeah.
Okay. Then how many oxygens do we currently have on the right?
8.
8. Good. Redemption. Okay. So, are we balanced? No. How do we fix this?
Add a 5 to the
5 in front
O2.
of the O2.
Yeah.
That would give us how many oxygens?
They'll add 10 oxygen. Then that's going to be 18.
18? Would this be 10? 10 oxygens?
Right. So now you add a 6.
Yeah. You got a
That'll be
6.
18. Yeah.
Perfect. Add a 6, 12 oxygens, and then we're balanced. Any questions on how that worked? Did I lose anyone anywhere?
Well,
Yes.
hold on.
Yeah.
So, right. Okay. No, it actually makes sense though. Yeah.
Yeah.
It is a little bit too many calculations there. Just
Yeah, there's a few little timeses, multiplications,
It
but
was oxygens.
yeah, it's the oxygens that really mess you up on these types of balances, things that occur on both sides.
Yeah. Well, it's the first time I see this, so it's good. It's all right.
Okay,
Yeah.
that's totally fine. If it's the first time you're seeing it, that's why these are here. You've got 10 examples to go through. I would highly recommend after this session, before the next one,
Mhm.
you go and practice through these 10 examples
Okay.
and get an understanding of what's going on. The answers are in the bottom right, flipped upside down, so you guys can't cheat to some extent. Don't tempt yourselves. All right. We're not going to touch these chemical reactions. These come back in module 3, so don't worry about these yet. But on to the start of module 1. So module 1, as I said, is the properties of matter. And the first inquiry question that we get asked is, how do the properties of substances help us classify and separate them? There's 3 dot points that we have to know, and these are all taken straight from the syllabus. So you can be guaranteed these are going to be coming up at school. So the first thing, we've already seen some of these today, ionic compounds, whilst we were doing the crisscross method. The dot point reads, to investigate the nomenclature, which is the naming of inorganic substances. Inorganic, don't really need to know what that means yet. It's basically everything for the time being. So investigate the naming of substances using IUPAC naming conventions. And that's just the convention we follow. So the naming of substances is this first dot point. We need to know how to name 2 different things: ionic compounds and covalent compounds. Can anyone kind of describe the difference between ionic and covalent compounds to start? What's the difference between ionic and a covalent compound?
Ionic is like metal and non-metal.
Good. And then what's a covalent compound?
Two non-metals.
Two nonmetals. Perfect. So we have ionic compounds, which are a metal ion bonded to a non-metal ion. And we have covalent compounds, which is a non-metal bonded to another non-metal. And these are named slightly differently. So the first thing we learn how to name is ionic compounds. Ionic compounds are very simply named. You have the metal always named before the non-metal. So it'll be something like sodium chloride. And I kind of gave away how you name the second part. All you need to do is change the non-metal. So for example, if it's chlorine, you replace the "ine" with "ide." Chloride. So you end up with a metal, non-metal ide. Magnesium chloride. Right? So then what would you call, Zenat, what would you call this? Calcium. And then what's this? Actually, I should change it. That's too easy. I just gave the same one. What's this? CaBr2.
Calcium boride.
Boride, not quite. This is Br. Boron would be B. Br. What's Br?
Bromide.
Bromide. Good. And then let's try another one. How about let's do Li. I don't know if this even exists. Go back to Xena. So the first one is lithium. The second one is I.
Is that iodide?
Yeah. So then lithium
Iodide.
iodide. Perfect. Makes sense? So that's how we name our ionic compounds. For when it's a non-metal bonded to a metal bonded to a non-metal anion. Anion meaning a negatively charged ion, as opposed to cation, meaning positively charged ion. Then the second case for these ionic compounds is where you have that where you have a metal bonded to one of those polyatomic ions we saw before. And this is why it's so essential we know those, because you need to be able to just kind of visually see them and be able to name them or create the formula. And these are even easier to name. You just say the metal, then you say the polyatomic ion. So if it was sodium bonded to a nitrate, sodium nitrate. Very straightforward. So then what would you call, let's say CaSO4? Mohammed, do you know your polyatomic ions? It's okay if you don't.
I can try.
Yep. Do you know what this
Is
SO4 is?
Is it sulfate?
Perfect. Sulfate. So then what
So
would you call
it's
this?
calcium sulfate.
Perfect. That's it. Brilliant. Does that make sense with the polyatomic ions as well?
Yeah.
The only exception here is when you have ammonium bonded to a non-metal anion. You just say ammonium as if it was the metal. So ammonium chloride, and you'd name the non-metal with the ide. Ammonium chloride, ammonium bromide. Any questions on this naming to begin with? Cool. And I should also explain what actually happens when you're making these ionic compounds, because we talked a bit about the outer shell of electrons before. We should really explain this. So with an ionic bond, an electron is what we call transferred from a metal to a non-metal. So the electron is transferred from the metal to the non-metal. So if we look at this atom over here is modeling the metal. This one is modeling the non-metal. What happens when these two come in contact is the electron from the metal moves and is donated to the non-metal. So if it left behind, if that electron left behind the metal, what charge does the metal have? Now that it's lost. What was that?
Positive.
Positive, positive, good. Perfect. The metal will be left with a positive charge. And then what charge does the non-metal gain?
Negative.
Negative. Perfect. And as we know, opposites attract. So we have a positive and a negative ion. We call the attraction between them an electrostatic attraction. Electrostatic attraction, and this forms our ionic bond. Does that make sense? Okay. And for covalent bonds, I will talk about in a second. The second things we need to name are covalent compounds. So when you have non-metals bonded together through electron sharing. So covalent compounds will share an electron to fill both of their shells, and this is only between non-metals. When you name these, they're a bit odd. When you're naming a covalent compound, the first non-metal is the one that lies furthest to the left on the periodic table. Furthest to the left. So for example, if you have a covalent compound with an oxygen bonded to a nitrogen, what do you name first out of these two?
Oxygen.
Oxygen. What was the rule?
Oh, to the left. Sorry, nitrogen.
Nitrogen, good. So we'll name nitrogen first. It'll be nitrous oxide. We've seen that before, but that's actually a bit of an exception. Nitrogen monoxide would be how we call it. Nitrogen monoxide. And that gives you a bit of a hint as to where we're going next. There's one exception to this. If elements are in the same group, so say you had sulfur and you had oxygen, the one that we name first is the one that occurs lower on the table. So it'd be sulfur dioxide, for example, like this, not the other way around, because sulfur occurs just below oxygen on the periodic table. So these are the first rules. Does that make sense for everyone?
Yeah.
Okay, good. And then secondly, we need to quantify how many of each atom we have, and we use a set of prefixes. The prefixes are as follows. If you know your, I guess, polygons, you might have a bit of a hint as to what these might correlate to. So mono, 1, di means you have 2, tri means you have 3, tetra, 4, and then these are all your pentagon, hexagon, heptagon. So if you know those, then you can remember the rest. So the first 4 you might have to remember, but otherwise they all just follow what you'd call polygons. Does that make sense what I'm saying with the polygons? Just a nice, easy way to remember it. So then, for example, if you had a molecule like NO2, as we just had above, NO2, the way we name this is you would think mono nitrogen and then di-oxygen, but there's a few final rules. It's that the first element, the only time it doesn't take the prefix if it's got 1. If it has only 1, then you don't need to say mono. So this would just be nitrogen, not mononitrogen. You don't say the mono, even though you think it. And for the second part, you have 2 oxygens. So it'll be di-ox. And we end the second element with ide, dioxide. Nitrogen dioxide. What is this? We've seen this before.
Carbon.
Carbon,
Oxygen.
Dioxide.
dioxide.
Yeah.
Good. So does that make sense how we got to those names? What if you had N2O2? Well, let's do N2O4 to make it interesting. N2O4.
Nitroxide.
Not
I don't.
quite. We name each bit
Oh.
individually. We name each bit individually. Good effort though.
But we don't say nitrite. I don't know. Nitrite, is it?
Not we'll name each bit. So
Ah,
the nitrogen bit and then the oxygen bit. So how do we name the nitrogen bit firstly? How do we say
nitrate.
yes?
Yeah.
Dinitrogen. This is not a
Okay.
nitrate ion. Nitrate is NO3.
Okay.
It's nitrate.
Mhm.
So this is what we call dinitrogen, first of all.
Mhm.
And does anyone have a hint as to what we'd name the oxygen part with 4 oxygens?
Tetroxide.
Yeah, tetroxide. Nitrogen tetroxide. Okay. Any questions on what we're doing here? Because this can be really tedious, these rules. Take silence as complete understanding. So, can we have a go at naming a few of these compounds? We'll go up the list. So, Mohammed, can you tell me what, first of all, Mg, oh, you've already had this. Do NaCl. What's NaCl?
Sodium chloride.
Sodium chloride. Soha, what's MgSO4?
Magnesium sulfate.
Good. Martha, Fe2O3.
Let me find what F is.
I'll tell you with iron.
Yeah. Oh yeah, iron, and like oxygen. So it's um di-iron, I guess.
Hang on. Which one do we use prefixes for? Covalent or ionic compounds? This one's mixing. This one's a bit confusing.
Oh, right. So
Hmm.
first with the oxygen, so it's trioxygen.
Wait, but we don't. Going back to ionic compounds,
Okay, yeah.
we don't need prefixes for these ones. We just name it as it is. It's really,
Oh, okay, yeah, sorry.
yeah. Then
Uh,
what would be this one?
it's oxygen. Oh, hold on, iron oxide. Hold on.
Yeah, that's it. Iron
Yeah, so you
oxide.
said
So,
first the oxygen and then the iron.
no.
Oh,
For
okay.
the ionic compounds, it goes metal, non-metal. And
Yeah,
this one's a
yeah.
bit confusing because Fe or iron is what we call a transition metal. It can occur with different valencies.
Mhm.
So when we see something like this, for the people who are striving for full marks this term, you want to always specify the valency of the ion. Can someone tell me what the valency of the ion is here? It's a bit of a reverse crisscross. What's the valency of the ion?
3.
3. Good. So we say iron 3 oxide. Bit of an extension. For now, if you can know that that is called iron oxide, you're already flying. If you can know that for transition metals, you also need to specify the valency, that's also a bonus. And lastly, Zenat, what's this?
Is that nitrogen and hydrogen? Like, I don't.
This is a polyatomic ion that we saw before as a hint.
Oh, um, hyd hydroxide.
Not hydroxide, it's actually ammonium. So how would you name this?
Oh, oh, ammonium chloride.
Perfect. Ammonium chloride. Great. And then now over to the covalent compounds. Let's go down the list now. Zenat, what's NO2?
That would be nit nitrogen oxide.
Oxide. Do we need to say how many things are in covalent compounds?
How many things?
As in how many atoms? For covalent compounds, do we need that prefix, those prefixes?
Oh, then oxygen has one.
Does it have one? NO2?
Oh, two.
Two. So what's the prefix for two?
Di.
Di. So what do we call this molecule as a whole?
Nitrogen dioxide.
Yes. Does that make sense?
Yeah.
Bit better? Okay. Martha, on to the next one.
Nitrogen
Nitrogen.
and do we say nitrogen oxide? Just that?
Okay, there's a something oxide, but we need prefixes. So what
Okay.
prefixes do we use?
Trioxide.
Trioxide. And then for the first one, this isn't a case where it only has one nitrogen, so we do need a prefix as well.
Dinitrogen.
So the whole molecule together,
How do we know that we need prefixes?
if it's a covalent compound, which means you have things that are non-metals. Oh, I should specify where you find non-metals as well.
Yeah.
Sorry. Non-metals are all of these metals over to the right side of the periodic table.
Okay.
These are all non-metals, but the ones you're going to worry about are these purple ones. If you have a compound which only contains atoms from this purple range, it is called a covalent compound.
Okay.
Does that make a bit better sense?
Yeah, yeah. So
Yeah.
just them are the covalent compounds?
Yeah. So if you had, for example, N and O, that would be covalent. If you had S and F, covalent. Cl and it's unlikely to have F, but if you had P and F, covalent.
Okay.
That makes better sense?
Yeah, yeah.
Okay,
Makes
good
sense.
question. All right. Soha, N2O5.
Dinitrogen. I forgot the prefix for oxide.
Think polygons.
Oh, pentoxide?
Yeah, pentoxide. So a little memory trick always makes things easier. Muhammad, what do you reckon SF6 is?
Is it sulfur hexafluoride?
Yeah,
I think. Yep.
gnarly. Does that make a bit better sense?
Yeah.
Okay. And how about we go back to Zena and Martha, do one more each. What's PCl3, Zena?
Phosphorus trichloride.
Bingo. Good stuff. And Martha, finish us off with OF2.
Oxygen difluoride.
Bingo. Brilliant. Does that make better sense now? Sorry if it was a bit confusing along the way. There's just a lot of rules. Okay, let's move. So we're gonna go a little bit over time today. Is that all right with you guys? Might go a little bit over,
Oh, good.
just because we have a lot to talk about. But the next dot point is mixtures and separation technique. So what are mixtures? What are the types of mixtures you can have? There are two types of mixtures, a homogeneous mixture and a heterogeneous mixture. So a homogeneous mixture is a mixture that contains substances that are completely evenly distributed. I actually want to change this definition. It doesn't have to necessarily contain, no, it does. Sorry. It's a mixture containing two or more substances that are evenly distributed with each other. So if you look at this diagram here, a homogeneous mixture will have completely even distribution of everything. And if you imagine a cup of salt solution, so NaCl in a beaker, all of the Na and Cl ions would be completely evenly distributed throughout. Completely even. That would be a homogeneous mixture. A heterogeneous mixture is a mixture where the two substances or more are not evenly distributed. So the diagram here showing heterogeneous mixtures being not completely uniform the whole way throughout. An example would be your bowl of cereal in the morning. You've got cornflakes kind of underneath, and then if you put too much milk, then you've got a layer of just milk covering your cornflakes. That would be heterogeneous. And as a bit of enrichment, because I always give you guys a bit more than you need. If you think about some certain mixtures, they can actually be both homogeneous and heterogeneous depending on how you think about it. So let's think about an example, which you're going to hear in both. And this is why it becomes very confusing sometimes. Let's think about air, the air that you breathe in, right? At sea level or wherever you are at the moment, your air has a composition of oxygen. It has a composition of oxygen, hydrogen, carbon dioxide, all sorts of gases in it, right? If you took a chunk of air from within your room right now, a chunk of air, this would be what we call homogeneous. It would be completely evenly distributed in your room. Inside your room, it's completely evenly distributed and homogeneous. But say you expand this sample and you take it as the entire atmosphere of the Earth, would you not say that the composition of air in your room is different to the composition of air at the top of Mount Everest? That's different, right? There'd be a lot less oxygen, as an example. So even though air can be considered a homogeneous mixture in your room, as a whole, air would be heterogeneous over the entire Earth because it's going to be different at different layers, right? So just be very careful when you describe a homogeneous versus a heterogeneous mixture. It depends on how you describe it as well, which makes it one or the other. Does that make sense?
Yeah.
Yes.
Okay. Types of matter. We have elements, compounds, difference between an element and a compound. Element is made up of only one atom, and these are always homogeneous. So if you had iron solid, this would look like this on the right, whereas a compound would be having two or more different elements. So you have sodium chloride, for example, would be a compound. And we've seen these already, covalent compounds, ionic compounds. These are also homogeneous. The big difference between a pure substance and a mixture, pure substances only have one type of molecule or atom. So these would be your compounds and elements are pure substances, whereas a mixture could contain a variety of different things, and they can be in any ratio. So a mixture would be for example, sand solution. If you have a bunch of sand in the bottom of a beaker, and you also fill it with water, this is a mixture. The mixture composition can change. So for example, I wanted to put in more sand, it's still a mixture of sand and water, but the composition has changed. For a pure substance, you cannot do this. You cannot change the composition. Its composition is fixed. So if you had a pure sample of just water, you would have two hydrogen molecules, or two hydrogen atoms rather, for every single oxygen atom.
Could there not be more of an element in the pure substance? Oh, but it's no, never mind. Yeah.
Yeah, so the
Yeah.
pure substance would just be one element. And if you were to add more, then you would just have more of the pure substance. Does that make sense?
Yeah, I was thinking the relationship between the homogeneous and heterogeneous, but yeah, it was a pure substance, so sorry.
Well, for the homogeneous and heterogeneous, are these pure? No, they're not. These are the mixtures, right?
Yeah.
So these could have all sorts of different composition. It just depends on how much you want. And this is what I wanted to cover today mostly, separation techniques. So when you've done experiments in the lab, you would have maybe over the last few years done one where you need to separate out certain components. So if you have a mixture of salt and a mixture of metal filings, you should be able to use different techniques to separate these substances. And we use what we call physical properties to separate them. So you might have heard of physical properties and chemical properties before, and not really been able to differentiate them. So let me make it clear. Physical properties are properties that will not change the identity of the substance. whereas chemical properties will change the composition of the substance. So a physical property, for example, is melting point. If you provide enough heat to a substance, the atoms will move fast enough to dissociate and start moving fast, as we talked about before, right? But those atoms or molecules themselves did not change in composition. They're still the same molecules. Does everyone follow that train of thought? Is that confusing? Anyone lost? It's okay. I can explain it again.
And then again, please.
Yes, I'll go again. I saw a confused face, so I wanted to make sure. So a physical property would be melting point, because as you provide heat to, say, a solution of water, solution of water has molecules moving around like this. As you provide more and more heat, these get faster and eventually they can start to break away and turn into gas. But did those water molecules themselves change in composition? No, they didn't change in composition. They're still H2O. So a physical property means no change in composition. But a chemical property, for example, hydrolysis, where you're reacting water or turning water into other things, if you are changing the composition of the substance, then that is a chemical property. The ability to be reacted is a chemical property.
Yeah.
So we're just talking about physical for now. Just talking about physical. Does that make sense?
Yeah.
Great question. So the ones that we're going to talk about in particular are firstly density, how much something weighs per unit volume. Something that's more dense will weigh more. If you had just 1 centimeter cubed, this might weigh more than 2 centimeters cubed of another substance. That is density. Melting point, the temperature at which a solid turns to liquid. Boiling point, temperature at which liquid turns to gas. Solubility is the ability for something to be dissolved in a solvent. It's going to be pretty hard to understand what isn't soluble at the moment with our current understanding of chemistry, but over the next year or so, you'll understand better. And finally, magnetism. Basically, is it a metal? Because most metals will be able to be attracted or repelled by magnetic fields. So these are the properties we're going to use. And also size of molecules, but this is quite intuitive. So the first method we're going to talk about is sieving. Think about if you're making a cake, you have your sieve for your flour. What's the purpose of that sieve? It's to make sure the very fine flour falls through and you're left with all the clumpy stuff at the top, so you don't get that in your cake, right? The same thing can be used in the lab to separate solids of different particle size. So if you have your sieve and you put your large particle and small particle mixture together, all the large particles will be captured by the sieve and small particles can fall through. That's our first method. So each of these methods, I want you to understand the property that we're using, the procedure itself, how we're doing it, and then what that setup sort of looks like. That's why I've given you a diagram on the right. Is that fair? Okay. Second, magnetic separation. So if you have substances that have differing levels of magnetism, for example, a mix of iron shavings and sand, you're going to be able to pull away the iron with the magnet and sand will be left behind. Pretty intuitive as well, right? And finally, if you have substances with different levels of solubility. So I'll get you to think about salt in your kitchen. When you put salt in pasta or any of your cooking that has water, just salt will dissolve, disappears into the solution. If you have substances which dissolve versus substances that don't, you can add water to get rid of the ones that dissolve. So for example, if you have sodium chloride, salt, and sand, if you add water to this mixture, you'll be able to dissolve the sodium chloride. So you'll have sodium chloride ions floating around in water. And you'll be left with a layer of sand at the bottom. And so if you wanted to get rid of the sodium chloride, you just tip out the water and you're left with sand. Does that last one make sense?
Yeah.
Yep. All good? Okay. Scale of 1 to 5, understanding those first three. Where are we? 5 being very understood, 1 being lost. 3, 4, 5, 5. Okay. Solid and liquid mixtures. So again, we're using properties to separate. So a solid and liquid mixture, the first property that we can use is when we have differing solubility, well, we have insolubility rather, of the solid in the liquid, so it doesn't dissolve, and the solid is also denser. If this is the case, we can use sedimentation and decanting. So firstly, sedimentation means letting rest, and as you let this mixture rest, this dense solid will fall to the bottom and collect. That's first sedimentation. Once you have sedimented this solid at the bottom, you'll have a layer of liquid on top and solid on the bottom. And this is when we can use our next method, which we call decanting. Decanting is essentially tipping off that liquid from the top. Tipping off the liquid, which leaves behind solid, and all of the liquid can be emptied out. Sedimentation and decanting. Does that make sense? Okay. Filtration, using filter paper to get rid of large insoluble solids. So if you've ever used filter paper before, you'll rest it in a funnel and pour through your solution, and inside that filter paper you get left behind with lots of solid inside, and the liquid is allowed to pass through into a separate beaker. So you're separating solids from liquids based on the solid size. Cool. And finally, centrifuging. If you have a solid and liquid of different densities, a centrifuge is a machine which spins around very fast, spins and spins and spins, and dense particles get cast to the edges, whilst less dense kind of collect a bit closer in. So what this would do is you're able to separate out dense solids and less dense liquids using the different densities. A very common example of this is with blood. We always use centrifuging for blood. So whenever you hear separating blood, think centrifuge. Okay. And then after you've centrifuged, you'd want to use that method we talked about before, decanting, because you'd have a layer of solid with some liquid on top. If you pour off the liquid and leave the solid behind, we call that decanting. Okay. And this brings us to our last three. When you have solids dissolved in liquids, we can separate these by evaporation. Evaporation, which means that if we heat our liquid and boil off the water, we'll be left behind with whatever salt was inside that water, or whatever was dissolved in the water. Does that one make sense as well? Good. And our last two, let's talk about separation funnel first. If you have liquids of different densities which don't dissolve in each other, that's the important part. They are insoluble, or what we say immiscible. You might see this word. Immiscible liquids which don't dissolve in each other. You can separate these by density. So more dense liquids collect at the bottom, less dense liquids collect at the top, and this allows you to create two layers. You can open up the valve, and this allows for the dense layer to pour through. Close the valve when that's all emptied, and you're left with the less dense liquid. The less dense liquid will be left behind in the funnel, and the more dense liquid would have passed through completely into the beaker. So that's separation funnel. The last one, distillation. Separating liquids by a boiling point. So if you have two liquids, say one boils at 60 degrees Celsius and one boils at 100 degrees Celsius, and they're both inside this mixture. if you heat the solution to anywhere between 60 and 100 degrees, the 60-degree boiling point solution will boil. Will the 100-degree solution boil? No, it won't. So it stays behind inside your flask, whilst your 60-degree boiling point substance is boiled off. So this one is going to rise up and pass into a separate apparatus, which is called a water condenser.
Mhm.
What this water condenser does is it passes cold water through itself. So you pass cold water through this condenser, cold water. And say this is like 25 degrees. What's this going to do to the gas that's passing through it?
Liquefied it.
Correct. It's going to turn it back into liquid because the water condenser is taking out heat from the gas. So you get back in liquid form your 60 degrees Celsius solution or substance. And that is how you separate liquids by boiling point. Does that make sense? That's probably the most techie setup of the lot. That one makes sense. We should be okay.
Mhm.
Okay. Again, scale of 1 to 5. How are those 9 techniques feeling now? 5, 5, 4. Okay, good. So lastly, let's do an enrichment. This is year 12 content. So if you guys can understand this, miles ahead. Fractional distillation. Basically what we just talked about, except a little bit even more techie. Fractional distillation is separating a mixture based on its boiling points. But in this mixture, you have many, many substances, more than 2. You might have 7, 10, 20 substances, all different boiling points. And one example we always use this with is crude oil in the real world. Crude oil, which is what you dig up from the bottom of the earth. You get a mix of all these fuels. So when you put crude oil into a fractional distillation device, the way it's set up is you want to think of it as a big vertical tube. It's a massive vertical tube, which is being heated at an extreme temperature at the very bottom. So at the very bottom, you're heating to 400 degrees Celsius, this crude oil. There are a few substances that have a boiling point over 400 degrees Celsius. So lubricating oil, paraffin wax, and asphalt, as examples, they don't boil. They stay at the bottom. But everything else does. So everything else will turn into gas and start to rise. Now, because the heat source is at the very bottom of this furnace, as you rise up this big vertical tube, the temperature of the air actually drops. So as you go further and further up, the temperature starts to drop and drop and drop and drop until at the very top, you're at atmospheric temperature, 20 degrees. Does that make sense?
Mhm.
So these gases will rise up. And at the temperature when they hit the altitude where the temperature is below their boiling point, they'll recondense. So fuel oil has a melting point of 370 degrees. At 370 degrees, it will recondense and drop back onto this specially designed tray, which allows gases to rise up through it, but doesn't allow liquids to fall back through. So the great thing is it will recondense onto this tray, and you can separate out fuel oil at this temperature, at this specific altitude in our tube. And guess what happens to the rest of the gases at this temperature? What happens to the rest of the gases?
They keep going up.
Keep going. They keep going and they keep going up until, let's say, 300 degrees, where diesel now falls below its boiling point. And so diesel condenses, you can collect this off.
So it has
Everything
to
else is
do
rising.
with different boiling points.
Exactly. Yes.
Yeah.
They're all different boiling points. And the tube, this massive vertical column, has different temperatures within it. And it allows it to separate all the different components of crude oil using boiling points. Much easier than doing a separate little reaction for everything. If you just have this massive column separate with boiling points, This is how it's done in the real world. That's why they have these massive tubes if you ever go to an oil refinery. Cool. Any questions on this setup? You've learned your first year 12 content. This is module 7. You'll learn this again later. It's not that bad, right? If you understand the basics, then you just grow on it through the years. So year 12 is just an extension of the stuff you learn in year 11, which is why it's important to understand stuff now. Okay. Very last exercise, and this will be the end of today. We'll go through the list, and you guys give me a suggestion of what you would use to separate these. So let's start with Mohammed. What would you use to separate sand and gravel, as shown here?
Can we use maybe a sieve?
Yeah, I'd use a sieve. That's very reasonable. What would you use to separate iron filings and solid sulfur, Soha?
The magnet one.
Yeah, magnet makes perfect sense. Non-metal and metal. Martha, sand and water. There are more than one correct answer for some of these, so be creative.
Yeah. Filtration.
Filtration works. Anything else?
I'm thinking that thing that was pouring down.
Uh-huh.
I forgot the name though.
Yep. Decanting.
Yeah.
The sedimentation and decanting.
Yeah.
Anything else? There's another one.
Evaporation.
Evaporation. Good. We can also do that. Evaporation. And I think, yeah, that's about it. If you really want to go over the top, you can centrifuge it, but it's already going to be sedimented for the most part, so you don't really need to do that. I kind of gave away the next one. Zena, what would you do for 4?
Is it called distillation?
I mean, technically you could. So technically it works because the plasma and blood will have a different boiling point. Yes, and centrifuge. But this is what I'm saying. There's more than one way to skin a cat. Distillation does work, but centrifuge is oftentimes what we'll use for a blood sample. Centrifuge and decant. And then back to Mohammed, salt dissolved in water.
Evaporation.
Evaporation, straightforward. These last two are a bit harder, so I'll open it to the floor. A mixture of ethanol and water.
Could we use distillation as well?
Can use distillation, perfect. Probably not anything else, to be honest. And then 7, a mixture of vegetable oil and water. This is a few solutions.
Oh, the separation funnel.
Yeah, separation funnel. Can use some other things. What else can we use?
Distillation.
Yeah, we can distill it as well. That works as well. The reason why we can't use separation funnel on ethanol and water is because ethanol is soluble in water. So if they wouldn't exist in 2 layers, they'd be homogeneous, as we learned earlier.
Yeah.
Right. So that's all I'm going to leave you with today. We've gone a little bit over time, so I do apologize, but it is the first session. There's a lot to cover. So from here, we've got 5 more sessions to cover all the content in module 1. Year 11 is just an annoyingly content heavy year. There's just a lot of random stuff. But if you understand from the bottom up what's happening, understanding will flow a bit more naturally once you get towards exams. Any questions before we finish up?
No.
What do we
Yes.
do after this?
What are you doing after this? You
Yeah,
have
how do we well,
consolidate.
yeah,
So I would, if I was you, I would go through and finish any of the questions in these notes that you haven't done in class, and you can test yourself on the questions we have done again. So if you haven't written the answers in, or if you get a fresh copy, test yourself again, and come up with things in the notes that don't make sense. That'd be a very good way to go and revise. Find things that don't make sense, and then ask me next time.
Yeah, that, and also what do we do in terms of your lessons? Do we pay the 700 altogether, or how many lessons is it?
Yes. so it's 8 sessions this term. There'll be 6 content altogether, exam week, and then exam review. So
Okay.
8 altogether, and then the payment I can discuss with you outside of class.
Okay, great. That's fine.
Cool. Any other questions, content wise?
All right.
That's a lot, I'd imagine, for a first session.
Yeah, it was a lot in terms of like balancing the equations, which I haven't done before, but it was alright.
Yeah.
I get better.
Yeah, I think you just need a little bit of practice, and then once you've seen a few and done a few, it'll come a lot more naturally.
Yeah.
But thank you everyone for staying over time. I do appreciate it. And I'll be in contact with you guys outside of class. Let me know if you have any questions throughout the week, and I'll be more than happy to help whenever they come up. All right. Well, we'll end it there, and I'll see you guys next time.
Thank you.
Thank you.
Thank you.
No worries. See ya.